This app shows you how to use quantile-quantile plot for normality, for normal distribution. So the idea is following. First of all, we have a sample, right? So by default, you can see the sample size is 6. And this is the values of my sample. It's just the height of 6 persons randomly taken from the population. What do? First of all, I compute the sample quantiles using the same way as I did it in the very first app. So I take, for example, I split the whole value to intervals, and then this value is in the middle of the first interval, this value is in the middle of the second interval, and so on and so forth. So you can see that, for example, the quantile value here it's 10%, the quantile value for this value it's 90%, right? And then these are my empirical quantiles. So these are quantiles I compute based on the values, okay, based on the position or based on the distribution of the values. So this is the first Q in the name of the plot, QQ plot. Now I can compute also theoretical quantiles. And in this case, I say, okay, if it's normal distribution, what's the border between 10% of smallest values and 90% of the largest values? So I can compute a z-score. So it tells me if you want to get a border, if you want to get the 10th percentile in normal distribution, you should take 1.28 standard deviations smaller than the average. So this will be my theoretical quantile, theoretical z-score for this value. So this value has two quantiles. It's the quantile of the empirical quantile and also z-score. That's a theoretical quantile. And then I simply do the same for all the others. So I compute empirical quantiles and z-scores, and then I make a plot. This is a z-score, and this is the real values. The idea is following. Normal distribution is not uniform, right? So the density is larger in the middle and then smaller on the tails. But here what I do, I sort of apply a CDF function, and then I apply ICDF function. And if I apply the real function and then the inverse function, I should have a linear dependence between the real values and the z-score, but only if indeed these points follow the normal distribution. This is not fully correct. 6 points cannot follow normal distribution because normal distribution is something about large numbers. So therefore the correct to say is that these points came from normally distribution population. So if indeed these points came from normally distribution population, then the z-score, and the real value should have a linear dependence. And that's what we check on the cuckoo plot. So you can see that this is the z-score, these are the real values, these are the points, and then you can see this is the line, kind of ideal line. So if we indeed have a perfect sample came from normally distributed population, all these points should lie exactly on this theoretical line. We have a pretty good agreement, right, in this case. So maybe this one looks a little bit like outline, right? The point is that this is indeed sample came from normally distributed population. That's the way I wrote this app. Then you can see that every time I take a new sample, the points sometimes will be pretty close to this line, sometimes pretty far from this line. But most of the time you can see they look, for example, this one, almost ideal, right? So in this case, I know they came from normally distributed population. And most of the cases, you can see that the cuckoo plot shows me that. So the cuckoo plot shows me that the points are exactly very close to this straight line. So in this case, I can confirm that, okay, visually at least, of course it's subjective plot, you need to make a normality test if you want to be a little bit more objective, but visually at least, these points look pretty much okay to the null hypothesis that indeed they came from normally distributed population, okay. What else you can do? You can also see the sample statistics and the population statistics. So this is mean and standard deviation of my population. This is the skewness. You remember that for normal distribution, skewness is 0 because skewness is a measure of symmetry. And if a distribution is perfectly symmetric, skewness is 0. And kurtosis is a kind of piggedness of your distribution. And for normal distribution, kurtosis should be 3. So this is the theoretical expected values. And this is the values I have for the current sample. So you can see this is the mean, a little bit smaller than that. Standard deviation is a little bit larger than that. Skewness is almost 0, that's okay, and then kurtosis is approximately 2 times smaller, right? But again, this is because my sample size is small, so sometimes these values can be even more extreme, right? So like, for example, in this case, you can see the kurtosis is okay, but skewness is large, and then you can also see the standard deviation is okay, the average is a little bit larger, right? These values will vary quite a lot, especially if your sample size is small. If your sample size is large, then the values will be much closer, the statistics will be much closer to the population, and also this variation from sample to sample variation also will be smaller. Interesting thing that you can also show the population in this case. So if you click on, you will see the real theoretical curve for the population. And then you can see how big the deviation is, right? So for example, if I take a sample size of 6, you can see how big the deviation is from the population, right? So the deviation is simply huge sometimes, right? But if you take sample size 12, then you can see the deviation is, in general, it's a little bit smaller. So the uncertainty or sample to sample variation rather, it's much smaller if you have a larger sample size, right? So once again, try different sample size, and then hopefully you will get a better feeling of how this quantile-quantile or QQ plot works.